So this is a RCC LSM design question. The question states that we have to design a beam of 500 cross 700 and the given data is width of support, live load and grade of concrete and steel and effective cover. So the first step would be to draw the cross section of the beam, which is going to be of course rectangular 500 cross 700. Also effective cover is also given to us. This is a representation, not absolute that there are 4 bars, just to represent the effective cover. So effective depth would be 700 minus 60, that is 640 So now the next step would be, since the size of beam is already given to us, we have to compare between two moments. First, moment of resistance of limiting section and factored bending moment of given section, because we already know the dead load and live load, so we can calculate the factored bending moment of the given section. So what is the formula for factored bending moment, which is going to be equal to 1.5 W L effective square divided by 8, where W is equal to summation of live load and dead load. So live load is given to us as 35 kilonewton per meter. Add 0.5 into 0.7 into 25 into 1, because 25 kilonewton per meter is the weight density of reinforced cement concrete. So the addition will come to around 43.75 kilonewton per meter. Okay, now we substitute it into the formula. The next thing would be to get the WU. It's 1.5 into the total load, because here we have to take partial factor of safety into account, because it's a limit state of design question. Now calculate L effective. It's going to be minimum of L clear plus width of support, or L clear plus effective depth. It is going to be the minimum of these two quantities. So width of support is already given as 0.3 meter, that is 300 and effective depth is 640 So substituting those values, minimum is going to be 6.3 meter. So now calculating factored bending moment by substituting it into the equation of factored bending moment, we are going to get around 3 to 5.582 kilonewton meter. Yes, now we have to just get the moment of resistance of limiting section. It's going to be QBD square. So the value of Q is 0.36 FCK1 minus 0.42 K into K, where the value of K is 700 divided by 1100 plus 0.87 FY. We should know the values of K directly, because we don't have time to calculate these things. So there are 3 cases for FE250, FE415, FE500. 0.148 FCK for FE250, 0.138 FCK for FE415 and 0.133 FCK for FE500. Okay, so the given grade of steel was Fe415, so we are going to substitute 0.138 FCK. Yeah, now I'll be substituting it into the QBD square. 0.138 FCK is 35, B is 500, D is effective depth, that is 640 So the value is going to come around Newton so we have to convert it into kilonewton meter. So after calculating, I am getting the result around 989.184 kilonewton meter. So now we know the values of moment of resistance of limiting section and affected bending moment. We can compare between two, so that we know that we are going to design an under reinforced section, limiting section, or an over reinforced section. So let's compare between these two values. Moment of resistance of a limiting section and factored bending moment. So moment of resistance for limiting section was 989.184, which is huge, greater than factored bending moment. So we are going to design a under reinforced section. So what do we need to design in it? Since most of the values are given, we only need to find out the value of area of steel. The unknown is only area of steel, which can be find out using two methods. One is direct formula and second is sequential method, in which you have to find XU and then find the AST. So there are these two methods. First is direct formula and second is sequential method. First is to get XU and then to find out the AST. Now we are going to find out through direct formula, which is AST is equal to 0.5 FCK by Fy 1 minus under root 1 minus 4.6 BMU upon FCK BD square into B into D. On substituting the values, 0.5 into 35 divided by 415, 1 minus under root 1 minus 4.6, factored bending moment was 3 to 5.582 into 10 to the power 6, because you have to find it into Newton mm, because the denominator is also going to come in Newton mm. On substituting the values of effective depth, that is 640 square into 500 into 640. So we have to solve it into calculator. We are going to find out the value around 1492.22 mm square. So substituting that value here, okay, 1492.22 mm square. And now we'll find it through the second method, which is the sequential method and the cumbersome method, which consumes a lot of time and energy. So here we have to find XU first. How can we find XU? We have to equate the factored bending moment equals to the moment of resistance capacity through the concrete section, that is 0.36 FCKB into XU D minus 0.42 XU. On substituting the values, we are going to get a quadratic equation. So we have to solve that quadratic equation. If you are having a good calculator, you can calculate it directly, but I'll be solving it through the quadratic equation, solving equation, and that is Sridharacharya formula, minus b plus minus under root b square minus 4ac upon 2a. So writing it into a simplified form, so this is the simplified form of the quadratic equation, minus b plus minus under root b square minus 4ac upon 2a. A is already 1. So here we will get two values. One value is going to cross 1000 mm, which we are going to neglect for sure, because the depth of the beam is already 700 mm. So how come the XU be greater than 700 mm? So 85.55 mm is the XU. So now we have to equate the tension force equal to compression force, 0.36 FCKB into XU divided by Fy into 0.87. Yeah, I forgot to write 0.87 Fy. Yes, Fy is 415 because the grade is 415 steel. So after getting this, we are going to get our value same. There is a difference of slight decimals, which is due to the error of the values which we have approximated while solving through Sridharacharya formula. If you are having a good calculator, then you will directly find the exact answer. Yeah, so now you can revise the whole steps of the question. Thank you for watching this video. Have a good day.